is Sravanthi, working as Assistant Professor of Chemistry in Institute of Aeronautical Engineering. Today we are going to discuss topic is electrode potential and electrochemical series. So in this topic we are going to discuss what is electrode potential and what is the difference between oxidation potential and reduction potential, and also discuss Nernst equation and its applications, and electrochemical series and their applications. So these are the topics today we are going to discuss. So first, what is meaning of electrode potential? So the tendency of metal to get oxidized or reduced when it is dipped in same salt or own salt of the solution is called electrode potential. It is represented by capital E. So the tendency of metal to get oxidized means loss of electrons or gain of electrons, that means reduction. So the tendency of metal to get oxidized or reduced when it is dipped in same own salt solution is called electrode potential. For example, here any metal, it is placed in same own salt solution. If this metal undergoes oxidation, so in this case, the metal ions may pass into the solution. For example, here we are taking metal. When this metal is dipped in this same own salt solution. So in this case, if in case this metal undergoes oxidation, it gives metal ions and loss of electrons because it is a oxidation reaction. So when this metal undergoes oxidation, then metal ions pass into the solution. But otherwise, if the metal undergoes reduction, that means the metal ions may get into the deposited over the metal. For example, here metal, it is a reduction reaction. Reduction means gain of electrons. So metal, if in case when we dip this metal in the same own salt solution, if this metal undergoes reduction, reduction means gain of electrons. So in this case, metal ions may deposit over the metal. For example, it is clearly explained by taking galvanic cell. Galvanic cell means here we are taking zinc and copper. Already we discussed last class. So in this zinc and copper, so here zinc metal, when we dip it in zinc sulfate solution. Why? Because any metal we can dip in same own salt of the solution. So here we are taking zinc electrode. So this electrode is dipped in same salt of the solution means zinc sulfate solution. So already you know that zinc always acts as anode according to electrochemical series. So when we dip zinc electrode in this zinc sulfate solution, it undergoes oxidation. So oxidation means it undergoes oxidation, then gives loss of electrons, and we pass into this zinc ions pass into this solution. So in this case, it develops oxidation potential. For example, copper. This copper electrode dipped in copper sulfate solution. So in this case, copper always acts as cathode, so it undergoes reduction. So reduction means gain of electrons. So this copper electrode, when we dip in same own salt solution, that means copper sulfate solution. So in this case, copper acts as cathode, so it undergoes reduction. So here copper gain of 2 electrons and deposited there as copper at cathodic area. So in this case, it develops reduction potential. But in this case, it develops oxidation potential. So what is the meaning of oxidation? If the ability of an electrode to give up electrons and become oxidized. When we dip zinc electrode in this zinc sulfate solution, so zinc always acts as anode, it undergoes oxidation, so that means loss of electrons, and it gives, when the zinc metal undergoes oxidation, this zinc metal ions pass into this solution. This zinc metal ions pass into this solution. So in this case, it develops oxidation potential. For example, copper electrode, when we dip in copper sulfate solution. So already we know that copper acts as cathode, so it undergoes reduction. Reduction means gain of electrons. So copper gain of electrons, that means copper metal ions deposited at cathodic area. So in this case, it develops reduction potential. So the difference between oxidation potential and reduction potential is called cell EMF. So now we will discuss. So what is the meaning of single electrode potential or electrode potential? Already we know that it is represented by capital E. E means electrode potential or single electrode potential. So what is the meaning of single electrode potential? How can we measure this one? So it is a measure of tendency of metallic electrode to loss, that means it undergoes oxidation, or gain of electrons, that means reduction. So when it is contact with a solution of own salt solution, just now we discussed already zinc sulfate, copper electrode dependent copper sulfate. So same salt of the solution. In this case only it develops electrode potential difference. So it is called single electrode potential. So the tendency of metal to get oxidized or reduced when it is dipped in same salt of solution is called single electrode potential. Here in this diagram it is clearly explained single electrode potential half cell reaction. For example, this metal is dipped in same salt solution. If this metal undergoes oxidation, in this case if this metal undergoes oxidation, it develops oxidation potential. If this metal undergoes reduction, in this case it develops reduction potential. So now we'll discuss standard electrode potential. So what is the meaning of standard electrode potential? It is represented by E naught, standard electrode potential. So how can we define the standard electrode potential? It is a measure of tendency of metallic electrode to loss or gain of electrons when it is dipped in same unsalt solution, but here we are maintaining standard conditions. So what are the standard conditions? Temperature is 25 degrees centigrade or 298 Kelvin. Temperature is 25 degrees centigrade or 298 Kelvin, and concentration is 1 molar concentration, and pressure 1 atmosphere pressure. So these are the standard conditions we maintain, and we can calculate the electrode potential of that electrode. So that is called standard electrode potential. It is the tendency of metal to get oxidized or reduced when it is dipped in same own salt solution of and it containing 1 molar concentration at 25 degrees with standard conditions. So it is called standard electrode potential. It is represented by E naught. So now let's discuss EMF. So what is the meaning of EMF? Electromotive force. That means the potential difference between two electrodes or the difference between potential of two electrodes is called EMF. For example, when we dip in zinc electrode in zinc sulfate solution, in this case it develops oxidation potential. For example, copper electrode dipped in copper sulfate solution, in this case develops reduction potential. So the potential difference between these two electrodes is called cell EMF. So how can we define this EMF? EMF equals standard reduction potential of right hand side electrode minus standard reduction potential of left hand side electrode. So here right hand side generally we are taking cathode and left hand side we are taking anode. So for example in this zinc and copper, zinc always acts as anode, copper always acts as cathode. So how can you calculate this standard electrode potential of this galvanic cell of zinc and copper? So cathode is E copper minus E zinc acts as anode. So what is the electrode potential of copper? 0.34 volts. And what is the electrode potential of zinc? Minus 0.76 volts. So its value is 1.1 volts. So in this way we can calculate the EMF of the cell, galvanic cell. So now we'll discuss Nernst equation. So what is the meaning of Nernst equation? So it was derived by Walter Nernst in 1889. So Walter Nernst here proposed Nernst equation in 1889. So according to him, this Nernst equation mainly explains the relationship between electrode potentials, temperature, and concentration of ions is called Nernst equation. So Walter Nernst in 1889 he was derived this Nernst equation. So this equation explains the relationship between electrode potential, temperature and concentration of the ions. So this equation is called Nernst equation. So this equation or the electrode potentials mainly depends upon the concentration of electrolyte solution and temperature. That means here we are maintaining standard solutions, standard conditions. That means concentration is 1 molar, concentration, temperature is 298 Kelvin or 25 degrees centigrade, and pressure is 1 atmosphere pressure. So we are maintaining the standard condition and we can calculate the electrode potential of that electrode. Okay, for example here, for the general reduction reaction occurring at an electrode. For example here, metal ions, gain of electrons then gives metal. It is a reduction reaction. For example, the general reduction reaction occurring at an electrode, that means here you are given reduction reaction, that means metal ions, gain of electrons then gives metal. So what is the Nernst equation? E means single electrode potential. It's equal E naught. Here Mn means metal ions by metal solid. Okay, it's equal E naught means standard electrode potential metal ions by metal minus 2.303 RT by NF log metal ions by products. Generally, what is the next equation? Here we are writing products by reactants. So next equation is, you can write E equal E naught minus 2.303 RT by NF log products by reactants. So we applied this equation for this reduction reaction. So here products are metal solid and reactants are metal ions. It is a reduction reaction. So we can apply this Nernst equation for reduction reaction of this cell. So here, so what is the Nernst equation for this soft cell reaction? E equal E naught minus 2.303 RT by NF log metal products by reactants. So metal solid by metal reactants, metal ions. So here E means single electrode potential, E naught means standard electrode potential, and R means gas constant. So its value, gas constant value 8.314 kilojoules. Okay, so E means single electrode potential, E naught means standard electrode potential, R means gas constant. Its value is 8.314 kilojoules, and T means temperature. Its value is 298 Kelvin or 25 degrees centigrade. Okay, and N means here number of valency electrons involved in this reaction. Number of valency electrons involved in this reaction. And F means Faraday. Generally 1 Faraday equal 96,500 coulombs. 96,500 coulombs. Here M means activity of metal in the metal phase is taken as unity. That means here metal products, it's taken as its value is unity, means it's equal 1. And metal ions, activity of metal ions in the solution is taken equal to their molarities. So substitute all these values in this above equation, that is equal E naught minus 2.303 RT by NF log products by reactants. So in this reaction, we can substitute all the R value, T value and F value. So finally we'll get this equation. So what is that equation? E equal E naught minus 2.303 into R value 8.314. 8.314 into temperature 298, and by N means number of valency electrons involved in this reaction, and F means Faraday. 1 Faraday equal 96,500 coulombs. So all these values substitute in this above reaction, and here already we know that M is solid phase concentration will always be taken as unity. So its value is 1. So substitute in this. So we can get 1 by metal ions in this reduction half cell reaction. So finally I'll get E equal E naught minus 0.0592 by N log 1 by Mn plus. So it's equal, we can write or otherwise E equal E naught plus 0.0592 by N log Mn plus. This is a reduction reaction. Nernst equation for reduction reaction. If in case this Nernst equation applied for this oxidation potential, in this case the sign will be reverse. That means the Nernst equation for oxidation half cell. In this case, how can write this Nernst equation? So E equal E naught minus the sign will be reverse. So minus 0.0592 by N log N plus. Okay. So this is the oxidation half cell reaction. Nernst equation for oxidation half cell reaction. So what are the applications of Nernst equation? So this Nernst equation is mainly used to calculate electrode potential of unknown metal. It is mainly used for determination of electrode potential of unknown electrode potentials by using this Nernst equation. And it is also used for determination of pH. And it is also used for finding valence of electrons involved in the reaction. How many number of valence electrons involved in the reaction. It is also we can find out by using this Nernst equation. So this Nernst equation mainly explains the relationship between electrode potential, concentration and temperature. So this equation is known as Nernst equation, and this equation is mainly used for calculation of electrode potentials. This symbol is E naught, standard electrode potential, or E, single electrode potential. And it is also used for determination of pH. And it is also used for find out the number of valency electrons involved in the reaction. So now I'll discuss electrochemical series and its applications. So what is the meaning of electrochemical series? So metals are arranged in increasing reduction potentials. Metals are arranged in increasing reduction potentials or decreasing oxidation potentials based on hydrogen scale. This series is known as electrochemical series. So what is the meaning of electrochemical series? The metals are electrodes or metals. What is the meaning of electrode? It is a metal or metallic rod which conduct electricity, which conduct electrons is called electrode. It may be anode or cathode. So these electrodes or metals are arranged in increasing reduction potentials or decreasing oxidation potentials on hydrogen scale. So this series is called electrochemical series. So how can you find out this electrode potentials? How can you calculate the standard electrode potential of other electrodes? So in this case, this unknown potential of electrodes, we know that electrode potential of that electrode. So that electrodes are coupled with standard hydrogen electrode. For example, we can find out the zinc electrode potential. So we don't know the electrode potential of zinc electrode. So this zinc electrode is, for example, this is zinc electrode. It is dipped in zinc sulfate solution. It is coupled with standard hydrogen electrode. So when we coupled with the standard hydrogen electrode, in this case, it detects electrode potential in this voltmeter. So in this way, we can calculate the electrode potentials of other electrode. That means any electrode, if what we have to find out the electrode potential of that electrode coupled with standard hydrogen electrodes. So in this case, we can detect the electrode potential in this voltmeter. So in this way, we have to find out the electrode potential of that electrode. Why we prefer only the standard hydrogen electrode? Because here we are taking standard hydrogen electrode is a reference electrode. Reference electrode means already we know the electrode potential of that electrode. It is used for guidance purpose, the reference purpose. So already we know the electrode potential of that electrode. We can find out the another electrode potential. So here we are taking standard hydrogen electrode is a reference electrode. Why you prefer only this standard hydrogen electrode? Because its electrode potential is zero at all temperature. Standard hydrogen electrode potential is zero at all temperature. That's why we preferred here standard hydrogen electrode is a reference electrode. So any metal, which metal electrode potential we can determine, that metal is we can coupled with standard hydrogen electrode. So we can detect the electrode potential that electrode in this voltmeter. So in this way we have to calculate the electrode potential of that electrode. Here standard hydrogen electrode is acts as a reference electrode. So reference electrode means already we know the potential of that electrode. So by using this one, we can calculate the another electrode potential. So here we couple with standard hydrogen electrode. Why? Because this electrode potential is zero at all temperature. So in this way we have to calculate the electrode potential of that electrodes. So all these electrode potentials arranged in increasing reduction potentials or decreasing oxidation potentials based on this hydrogen scale. So this series is called electrochemical series. So this is a series. So based on this hydrogen scale. So its electrode potential is zero. So electrodes are arranged increasing reduction potentials here and decreasing oxidation potentials. Increasing reduction potentials or decreasing oxidation potentials based on this hydrogen scale. Here hydrogen electrode used as a reference electrode. So this series is known as electrochemical series. In this series, above the hydrogen scale, all these metals are having anodic nature. All these are having negative reduction potentials and these metals were acts as anode. That means all the metals above the hydrogen scale, these metals are having anodic nature. And below the hydrogen scale, these metals all are having cathodic nature. That means these metals are acts as cathode. So this is most important. In this electrochemical series, above the hydrogen scale metals, those metals act as anodic nature, and below the hydrogen scale, those metals are having cathodic nature. So acts as cathode. This is a electrochemical series. So what are the applications of electrochemical series and its applications? So here we are given 6 applications. One is calculation of standard EMF of the cell, relative ease of oxidation or reduction, and displacement of one element by other, and calculation of equilibrium constant and hydrogen displacement behavior, and predicting spontaneity or feasibility of redox reactions. These are the applications of electrochemical series. Now let's discuss how can we determine the calculation of standard EMF of the cell by using electrochemical series. So how can you determine EMF? The standard EMF of a cell, that means he cell, it can be calculated if we know the standard electrode potentials values. So we can calculate the EMF of the cell. If we know the E0 values of that electrode, easily we can calculate E cell. So how we know that the electrode potential values? By saying this series. By using this series. So if we are using that series, we know that electrode potential values. If we know the E0 values of that electrode, easily we can calculate E cell. So calculate EMF of the cell. So what is the formula? E cell equal E0 RHE minus E0 LHE. That means E0 RHE. That means right hand side we can use cathode. reactions always we can write in an right hand side, and LHE means left hand side. You can take cathode. For example, we are taking zinc and copper. Already we know that electrode potential of that electrode by saying this electrochemical series. So here, according to electrochemical series, zinc present above the hydrogen scale. So already we know that above the hydrogen scale metals all are having anodic nature. That's why it acts as anode. Above the hydrogen scale metals acts as anode. Zinc present in this series above the hydrogen scale. So that's why it acts as anode. So here we are taking left hand side zinc. Here E cathode minus E anode. So cathode we are taking copper, anode, zinc. Why? Because in this electrochemical series, zinc present above the hydrogen scale, it is having anodic nature. So that's why it acts as anode. And here, copper acts as cathode. That means it is present in this electrochemical series below the hydrogen scale. So that's why it acts as cathode. So by saying this electrochemical series, already we know that E naught values of copper, that is plus 0.34 volts, minus E naught anode. Here we are taking zinc. Its value is minus 0.76 volts. So its value is 1.1 volts. So in this way, we can calculate standard EMF of the cell by using electrochemical series. That means if we know the electrode potential values, easily we can calculate EMF of the cell. How can we know that E naught values? By using this electrochemical series. Already we can given electrode potentials of that electrodes when we coupled with standard hydrogen electrode. So this is one of the application of electrochemical series. Now we can discuss second application of electrochemical series, that is relative ease of oxidation or reduction. Relative ease of oxidation or reduction means comparison of oxidation or reduction. So that means in this series, higher the value of standard reduction potential, to which metal is having high reduction potential, high positive value. So that metal is always try to get reduction, to reduce. Always that metal undergoes reduction only. It is a natural tendency of that metal. Or otherwise, if in case that metal is having high negative reduction potential, high negative value of that electrode. So in this case, always that metal try to get oxidized. That is natural tendency of that metal. So it is easily we can understand by using this electrochemical series, and which metal is having high oxidation potential and which metals is having high reduction potential. Easily we can understood by using this electrochemical series. For example, in this series, fluorine is having high positive value. That means high reduction potential. So in this case, that means here plus 2.87 volts. So in this case, fluorine is always try to get reduced. That means it undergoes reduction only. Why? Because that is a natural tendency of that metal. It is having high reduction potential. That's why always that metal try to get reduced. For example, here taking lithium. It is having high negative reduction potential. Its value is minus 3.01. So that metal, that lithium metal, always try to get oxidized. That is the natural tendency of that metal. So in this electrochemical series, which metal is having high oxidation potential, which metal is having high reduction potential, which metals easily undergoes oxidation or reduction. It is easily we can understood by using this electrochemical series. So in this way we can calculate the relative ease of oxidation and reduction. That means easily we can understood by which metals easily undergoes oxidation or reduction. Now we will discuss displacement of one element by another or other. So in this, how can you determine which metals are easily displaced elements by other? So in this case, the metals which are higher in the EMF series, which are higher position in electrochemical series, that metals only can displace those metals which are below in the EMF series or electrochemical series. For example, in this same example, we are taking zinc and copper. Okay, zinc is present above the hydrogen scale or zinc presence above the copper metal. So when we use this reaction, zinc, when it reacts with copper sulfate, so in this case, zinc is easily displaced copper. Why? Because zinc is present above the copper. So that's why zinc is displaced copper from this solution. In this case, it gives zinc sulfate plus copper. So which metals are present at higher position in this electrochemical series? That metals are easily displaced below the metals in this series. So which metals are higher position in the electrochemical series? Which metals are below in the EMF series? It can be easily understood by using this electrochemical series. This is one of the application of electrochemical series. For example, Fe and copper sulfate. So in this case, Fe presented above the copper. So that's why Fe displaces copper and then it gives FeSO4. Why? Because Fe present above the copper. That's why this Fe displaces copper from this electrolyte solution. Okay, so displacement of this iron, copper by iron. Why? Because it is higher position in electrochemical series than copper. For example, zinc and magnesium sulfate. In this case, there is no reaction. Why? Because zinc is present below the Mg and Mg is present above in this series. Zinc is present below of the magnesium in this series. So that's why zinc does not replace magnesium in this magnesium sulfate. So that's why there is no reaction. So what is the meaning of this one? So metals, any metals which are higher in the EMF series. So those metals easily displace which are below them in the electrochemical series. So which metals are above or which metals are below in this series, it is easily we can understand by using this electrochemical series. Now let's discuss calculation of equilibrium constant. So how can you calculate equilibrium constant? The symbol is K, equilibrium constant. So the standard electrode potential E naught. How can you determine this E naught? E naught equal RT by NF ln K. Here K is the equilibrium constant. So E naught equal RT by NF ln K EQ. So here R means gas constant. So already we know that value 8.314 kilojoules. T means temperature. Temperature means its value 298 Kelvin or 25 degrees centigrade. And N means number of valence electrons involved in this reaction. And F means 1 Faraday. 1 Faraday equals 96,500 coulombs. Okay. Here K means equilibrium constant. So here by using this electrochemical series, we can calculate the equilibrium constant. So here it's equal, you can write 2.303 RT by NF log K, equilibrium constant log K. So here we can calculate log K, equilibrium constant value. How can you determine this one? So log K equal NF into E naught by 2.303 RT. So already we know that N value, F value, E value, R and T. So substitute all these values in this formula. That means, for example, here N means number of valency electrons. Number of valency electrons. So F means 1 Faraday. 1 Faraday equal 96,500 coulombs. And E naught. E naught means standard electrode potential. Standard electrode potential. And R means gas constant. Its value is 8.314 kilojoules. So substitute all the values and temperature here. 298 Kelvin or 25 degrees centigrade. So substitute all these values in this equation. Finally, you'll get this one. So log K equal N E naught by 0.0591 volts. Here N means number of valency electrons and E naught standard electrode potentials. So in this equation, if we know the E naught value, easily we can calculate the equilibrium constant. So how we can determine this electrode potential? How we know that E naught values? By using this electrochemical series. Why? Because we are arranging all the metals, increasing reduction potentials, decreasing oxidation potentials based on the hydrogen scale in this series. So by using this electrochemical series, we can easily calculate the log K value, equilibrium constant value. So in this equation, if we know the E naught values by using this electrochemical series, easily we can calculate the equilibrium constant. So now we'll discuss hydrogen displacement behavior. Hydrogen displacement behavior. So metals which are higher position in electrochemical series, those metals are having high reactivity nature. For example, zinc, magnesium, these are present above the hydrogen scale. So these metals are having high reactivity nature. So metals which are having negative reduction potential. So the metals which are present in above the hydrogen scale in this electrochemical series. So that metals will displace the hydrogen from acid solution. That metals easily displace hydrogen from acid solution. For example, here zinc. This zinc is easily displace hydrogen from acid solution. Why? Because zinc is present above the hydrogen scale in this electrochemical series. So this zinc is having high reactivity nature. So this metal easily displaces hydrogen from this acid solution. So then it gives zinc sulfate level hydrogen gas. It displaces hydrogen from this zinc sulfate acid solution. For example, here silver, it is present below the hydrogen scale. So this silver metal does not replace the hydrogen from acid solution. Why? Because what is the reason? Which metals are higher position in electrochemical series? Those metals are having high reactivity nature. So that's why those metals only replace hydrogen from acid solution compared to below the hydrogen scale metals. So that's why here zinc is present above the hydrogen scale. So this zinc is having high reactivity nature. So when it interacts with H2SO4 acid solution, so zinc easily replace hydrogen from acid solution. But silver, it is present below the hydrogen scale. So it is having less reactivity nature comparatively zinc. So when it interacts with H2SO4, it does not replace hydrogen from this acid solution because it is present below the hydrogen scale in this electrochemical series. So by using this electrochemical series, which metals are present higher above the hydrogen scale are having high reactivity nature, or which metals are easily replaced hydrogen from acid solution. Easily we can understand by using electrochemical series. Now we'll discuss predicting spontaneity or feasibility of redox reaction. Redox means both oxidation and reduction reactions takes place. Here, for example, here spontaneity of redox reaction. Spontaneity of redox reaction, it can be predicted or calculated from the EMF value of the complete cell reaction. So, can we calculate the spontaneity or feasibility of the redox reaction? It can be predicted from the EMF value of complete cell reaction. For example, if E naught of the cell is positive, E naught value is positive, so the reaction is spontaneous. E naught value is positive, so the reaction is spontaneous, feasible. If the E naught value of the cell is negative, so in this case, it is non-spontaneous or not feasible. So how can we get this? Which reaction is spontaneous, which reaction is non-spontaneous? By using this electrochemical series. For example, if we are taking zinc and copper. So already we know that according to electrochemical series, zinc acts as anode, copper acts as cathode. Okay, so zinc undergoes oxidation, then gives zinc metal ions and loss of electrons. Copper acts as cathode, so copper metal ions gain of electrons and gives deposits copper. Okay, so here what is the EMF of the cell? E cell equals E naught cathode minus E naught anode. So here E naught cathode, so its value is copper value 0.34 volts plus 0.34 volts minus E naught anode. Here zinc acts as anode, so its value is minus 0.76 volts. So it's equal plus 1.1 volts. 1.1 volts. So E cell value is positive. So this cell reaction is spontaneous. So this cell reaction is spontaneous. For example, if we are taking copper and zinc, that means here copper acts as, for example, copper acts as anode. Here zinc acts as cathode. So in this case, what is the EMF of the cell? E cell equals E cathode minus E anode. So here we are taking E naught cathode, means in this cell zinc acts as cathode, and here E naught anode means copper. So what is the reduction potential of this electrode? Zinc. Negative reduction potential of zinc is minus 0.76 volts, and E naught value of copper is plus 0.3 volts. So what is the value? Minus 1.1 volts. So E naught value is negative 1.1 volts. Negative value means it is non-spontaneous. So it is also clearly explained by using this electrochemical series. In this way, we have to calculate spontaneity, that reaction is spontaneous or not spontaneous. Okay. So this is a electro. For example, here we are taking zinc and copper. Zinc acts as anode, copper acts as cathode. In this case, you can get plus 1.11 volts. So E naught value is positive, means it is spontaneous. For example, you are taking copper and zinc. Here copper acts as anode, zinc acts as cathode. If in this case, E cell value is negative 1.1 volts. So this negative means this cell reaction is non-spontaneous, not feasible. So how can you get this spontaneous or non-spontaneous? We can calculate this E naught value is positive or negative. So by taking E naught values from this electrochemical series, easily we can calculate E naught value of the cell, under which cell reaction is spontaneous or non-spontaneous. So today's class, we discussed already what is electrode potential, what is the difference between electrode oxidation potential and reduction potential, and also we discussed Nernst equation. Nernst equation for half cell reactions. What are the applications of Nernst equation? And also we discussed electrochemical series and their applications. Thank you.
Like, share and subscribe. hit the bell icon for more updates.